And today we are touching substations. Da, 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 da. Oh, what a brilliant animation. Oh my goodness. Oh. Hello and welcome. Let's talk about these guys over here, your CTs, your VTs, your circuit breakers, your disconnectors. Yay. You know, have you ever looked at ECV? Because it's ECV. ECT, VT, and then you wonder what is the difference? How do you identify a CT from a VT? You know? So what are they? So look at this overview, baby. Look at this, Nana. Oh, woo! Look at this. Beautiful, ne? Somebody was like, oh, please do this, do this. And I was like, I'm going to do it. Now, today we're going to be discussing overcurrent protection. And this is going to be a 2 or 3 part series because, hey, there's a lot to be learned, eh? So overcurrent protection is often the first line of defense, protecting networks against faults. In this video, we're going to look at the basic principle of overcurrent protection. And our starting point has to be the electromechanical relay because much of the terminology required to understand and operate modern digital relay has a physical meaning which can only be understood this way. Yabo? So the fundamental principle of overcurrent protection is to continuously monitor the current on the system, and it is seen if it sees it too high, definitely it will disconnect your feeders, right? Aha. So now the measurement of the current is done by none other than your CTs. So today we're going to be discussing the CTs, ne? And also we're going to be reviewing Uguti, hey, how can you see a CT and a VT? So we're going to be talking about CTs. So this steps down, ECT, ne? ECT, this is what it does. It steps down the current to a low enough level to be measured properly. And then basically transfer the information to your relays. So your relay now, it becomes your information point, and your relay will send you information to say, hey, we have a problem here, we have a problem, and it will send it to your none other than your circuit breakers. Aha. So now it will send it to your circuit breakers, and your circuit breakers will disconnect the faulty part of the system, right? And of course, your circuit breaker has got the physical ability, if instructed, to break the fault current and disconnect the faulty part of the system, also known as your disconnectors and your transformers, as shown here. But they are not the critical part of a protection system that we're going to talk about today. So we're not going to be discussing them today. So we're going to be talking about the current transformer, also known as your CT. So we know that your CT has the ability to step down your current to a very measurable, appropriate lower value. This is absolutely necessary because the fault current is way too high to be measured directly. In fact, impossible. Now the CT is very much like a standard transformer, where the line is the primary and we can construct a secondary with the number of turns we require to step down the current. Now, we also have the second part now, the electromechanical relay. Right. So this secondary CT current is actually fed straight into the relay and has a direct effect on its operation. So we'll go into more details on the current on the relay later. But so in the case of 100 amps, as you can see on the video is flowing, we know that there's going to be a 5 amps on the CT secondary inside the relay, right? So let's take a look at what happens when we have 200 amps line current and 10 amps relay secondary current. So now the current through the relay has generated a magnetic field inside generated a magnetic field which induces a torque in an induction disk. So it has got a disk. So the induction disk therefore rotates, and if it rotates far enough, a rotating arm hits the contact, and this initiates the instruction to the breaker. Remember, we said the breaker waits for instruction. So it waits for instruction from the relay. So the relay gives a command. So your relay is just there to monitor in case of a fault. So in anything, we have a threshold, right? So the breaker operates under a threshold and for a tripping signal. And the higher the fault current, the higher the relay current, and the stronger the deflecting force on an induction disc will be. So the relay will operate faster for a higher current. So we also note that the operating time depends on the distance the rotating arm needs to travel. And we also know that the sensitivity of a relay to the current can actually be changed. And these 2 points are actually important because they also allow us to configure the relay to suit a particular value. So this is very important. It's like replacing a breaker, go substation. You cannot replace a breaker because it has the same voltage range. You need to check your operating time. So this is an indication, Oguti, there is a time tripping for yonke int, all right? So look at your graph. If you have 20 amps, now your minimum operating time will be about 1 second. So it means it will trip faster the higher your fault current, right? So you have to configure this due to a tripping time before you burn things. So consider your sensitivity of your current as well. There's this thing what you call your plug settings, right? This is what you do when it comes to how much do you want your relay to be sensitive. The higher the lower the plug settings, the more sensitive your relay. And the higher the plug settings, the less sensitive your relay is. Example, if you plug it on 100%, so that's equivalent to 5 amps. And if you plug it to 200, which means a 10 amp current settings, right? And if you plug it to 50%, that means you require only 2.5 amps to move the disk, right? So this is the sensitivity. So you need to configure it in a way that you understand what will happen when it comes to tripping. So you can have a look here on your graph settings as well, as I've mentioned. So now what does this mean? The position of the plug, right, of the plug determines how many turns couple into the magnetic core, which helps to induce the torque into the disc, right? So the higher the plug settings, the less sensitive the relay is to the current. In fact, the pickup current, that's the current necessary to make the disc move, is it should align according to your plug settings. Remember,
Current we measure it go series and voltage go parallel. So therefore it means that the identification of ECT and AVT will be ECT right here. This is your CT. If you can monitor, there are two wires coming in and coming out, your primary and secondary. So this is your CT. This is how you identify your CT. But now your VT does not have that, right? Your VT doesn't have that. Your VT only has one connection point. One connection point, which is that one. So this is how you identify between the two, ne? And AMA VTs, they're always connected in parallel. And CTs in series, ne?